Okay, thanks so much, Siobhán. And well, thanks, Siobhán, for really taking care of this AI Nurses Network. And I'm sure everybody in this call might have received a lot of emails and info from you. You're really doing a great job with this AI Nurses Network. So as you know from Siobhán, today's workshop or lecture or presentation is on the basics of artificial intelligence in nursing research. And I'm maybe going to talk you through different types of learning that could be done with data that you might have available. So we'll be more like understanding the type of analysis using AI that could be done with data collected in healthcare or in any health environment. Just to introduce myself, I'm Crina Grosan, and I am part of the same division as Siobhán is, which is called Digital Health and Applied Technology Assessment, part of the Faculty of Nursing, Midwifery and Palliative Care at King's College London. So what we expect you to learn from today's lecture is to have an understanding of the main aspects of artificial intelligence and how it can be applied to healthcare research, to understand the difference between different concepts that are used when we deal with data analysis. And it's not just data analysis, we also use the term that is called data mining, data science. And we'll show you an example, a very simple example. It's a data science project. You will understand why it's data science and what that means. And it's a step-by-step. I will take you through each of the steps from having some data to making sense of that data and doing something with the findings from looking at that data. I told you earlier about a few data fields, which was data analysis and data science. Now, what they mean, maybe most of you have heard of data analysis, and when you read a research paper or you look at any publication, you see that there is some analysis in that paper. The data analysis term in AI or in the field of computer science statistics basically refers to some very basic data analysis that uses descriptive or maybe even some inferential statistics, some data visualization, and is meant to extract some insights from that data. So it's just looking at the data, finding something in that data that could be found with statistics, as I said, and simple visualization tools. And the output of this is usually some reports or some trends, some associations, sometimes some correlations you can find in the data. Data science is a lot more advanced, and it deals with a lot more complex problems, sometimes with data files that maybe you can't even open on your computer and see what is inside. It uses some statistics as well, but it also uses machine learning, some predictive modeling. And by predictive, I mean it looks at some data that you have, but then could also make predictions on some unseen data, similar to the one it looked at, which can be done with just simple data analysis tools. Machine learning is a subset of artificial intelligence, and I'm going to use the term a lot. Many times, computer scientists use machine learning when they work on extracting any features or any patterns from the data and not AI. In the life sciences and healthcare field, AI is mostly used, even if there is a machine learning analysis on the data. So it's broadly used in healthcare. But machine learning is a subset of AI, and it deals with algorithms that are meant to discover some patterns in the data. They could do predictions, they could do some discriminative analysis, like classifying the data or clustering the data. They're slightly different. Both classification and clustering put the data into groups, but the way in which they do it is slightly different. And then artificial intelligence is the largest of all. And in addition to machine learning, it also includes autonomous systems, so systems that can learn on their own. And you can think here of chatbots or even the robots and other bionic things. So it's a lot larger than machine learning. It includes not just software, but it includes also a mixture of software and hardware. It is basically meant to mimic human intelligence in all possible ways. There is this sequence of data analysis, data science, and then AI in terms of complexity. Now, there's also a term we use a lot when we deal with data, which is data analytics. And this is a bit different from data analysis. So if you just do data analysis, you look at the data and you want to find something, some patterns, or to discover something in your past or current data that you have. And the goal of data analysis is to answer questions like, for instance, why did patient readmission increase last quarter? Methods, as I said, include descriptive or inferential statistics, and it's mostly an exploratory data analysis. In addition to just exploratory analyzing the data, you could also use visualization tools. So unlike numbers, visual tools are more, how to say, are more descriptive about your data. So I like to see a lot of visualization when I do data analysis rather than just seeing a table with numbers in it. Data analytics is more complex, and I'm saying these terms and the difference between them just in case you do a database search for a certain topic and you want to get more than just simple data analysis. So analytics, in addition to just basic analysis, does a lot more, does predictive insights. It answers questions like, how can we reduce readmission next year? So rather than just looking at why patient readmission increased, they can also look at what can we do to reduce the readmission. So it's a lot more complex question that could be done. And it uses machine learning models in addition to the basic statistics. In between those, data analysis, data analytics, and the advanced data science that I mentioned is also a topic that is called data mining. Data mining looks at patterns in the data. It also uses machine learning and other pattern recognition tools. It deals with larger data sets than data analysis, and it finds associations and other high-scale correlations within the data. Just as an example to show you the difference between the three of them, in a data analysis example will be diabetic patients have higher readmission rates. In a data mining approach of the data, patients with high HbA1c and low exercise form a high-risk cluster. And a result of a data science applied to a data set will be an AI model predicts high-risk patients and triggers nurse intervention. So it is not just prediction, it also triggers some intervention in a data science. So data science is the most complex thing. Now, why I'm telling you all these things? Because depending on who the authors or co-authors of a paper are, various terms will be used for what is done inside this paper. So maybe most of the time in a paper that is co-authored by mostly life scientists or nurses or doctors, you will find data analysis. And maybe if they use AI, you will find the term AI. But if there are computer scientists or advanced statisticians, or if the paper, the majority of the authors are data scientists or computer scientists, then you will find other terms such as data analytics or data mining or data science or machine learning. So this will help you retrieve publications that address a certain topic by using additional keywords in your search or additional terms in your search. Now, when to use which of this data analysis, data mining, data science? As I said, data analysis is the basic analysis of the data. We usually use this when we want some quick answers and we want some descriptive reports. So they tell something about the data, how your data looks like. We use data mining when we want to explore some unstructured features in the data, or even the data itself could be unstructured. Finding some unknown relationships that won't come up if you just look with your statistical tools as part of the data analysis. Data science is more like a project. So you look at the data, you do all kinds of predictions and learning from the data, but you also come up with some solutions. So it's not like saying what you discovered in the data, is also even making some recommendations or coming up with some solutions that could help with clinical decisions or could support clinical decisions. And just some key aspects: data analysis explains the past, data mining discovers the unknown, and data science builds for the future. And I'll show you the difference of the outcome of all these types of analysis in a simple example. So let's say we have this example: reduced 30-day readmission for heart failure patients. In a data analysis approach, so remember, data analysis is the very simple one, the goal is to understand historical readmission patterns. So you look at the data and you see what patterns are there that make a patient be readmitted within a certain period of time. They could look at the data by age, by gender, by other comorbidities, look at trends. So for instance, patients with chronic kidney disease have 25% higher readmissions. Tools that could be used are even the simple Excel could do that, but could also be some other tools like Tableau, Stata, and so on. And the outcome could look like this. Heart failure patients with renal failure are 2 times more likely to be readmitted. So this is the kind of outcome they could produce. Now, it's not just this, but there could be other associations they can find within the data, but they all of this nature. As a limitation, it could identify some correlations, but there's no prediction or no actionable predictions. Now, if we look at that same data with a data mining approach, the goal will be to discover hidden risk factors or some patient subgroups. The methods could be some that we classify as machine learning methods. So for instance, this cluster analysis is a machine learning method. It groups patients, it put patients into groups based on similarity. So a cluster analysis could identify high-risk patient profiles. So for instance, let's say you get more clusters. One of the clusters, which is cluster 3, puts together patients with low sodium and high BNP and elderly. Could find some association real mining, like patients prescribed drug X and drug Y have 40% lower readmissions. Now, we need to move beyond the simple tools if we want to get these outcomes, and programming languages. And I mentioned here Python and R because they are the easiest one to use, as they have a lot of inbuilt libraries for data mining approaches and for machine learning. And I think they kind of easy to master if you know a little bit of programming. Even if you don't, you could do some very simple things with Python and R. And the output of the data mining approach could be something of a subgroup, which is 15% of patients with elevated troponin plus anemia, accounts for 50% of readmissions. So you see it's a lot more complex outcome that could be delivered. Now, the limitations of a data mining approach is that it finds these patterns, but doesn't predict anything for the future or doesn't intervene. Now, if you do a data science approach, the goal is to predict and prevent readmissions in real time. So you can determine what contributes to somebody being readmitted, predict when another patient will be readmitted, but could also take some actions to prevent readmissions. Now, what the data science approach will do, well, we'll merge multiple types of data. We call it multimodal data. Multimodal means multiple types of data, and could be electronic health records, which in itself is a multimodal data type because it has numbers, it has text, it has images sometimes. We have socioeconomic data, for example, and we could have data from wearables. And again, the wearable data is complex enough data. It could, I mentioned train an interpretable machine learning model to predict risk score, and I will tell you later on what this training means. But it could basically create a machine learning model that can predict the risk score for somebody of being readmitted. And in addition to that, it could even deploy an alert system that could be integrated with the electronic health record system, or with other electronic system or digital system that is in place that can alert the system when someone is at risk. And then an action could be taken. And again, we need slightly more complicated tools that we do for data analysis, some programming platforms. If the data is very large, and it usually that's the case, especially if you have multimodal data and you need to do the data integration, even some cloud platforms. But the output is a lot more complex, and it could be something of like a real-time dashboard flags high-risk patients at discharge and suggest interventions. So for instance, schedule a renal consult, and this reduces readmissions by 20%. So you see it's an end-to-end solution. It looks at the data, it can predict what happened to someone, and it can flag that something might happen to a certain patient. Data science, I would say, is the field that you need to be aware of, especially as most of the time you collect some data and you find something from that data, but not with the scope of just looking at that data, with the scope of having an impact in the future and having suggesting an intervention or contributing somehow to what you've learned from that data. So it's not, most of the time it's not a one-off analysis of the data. You want to do something with your analysis, and you want to maybe contribute to an intervention or to prevent something in the future. And I think that data science is the ideal approach for that. The tools that are included in data science and the tools that data science projects deal with could solve very complex problems, could combine the statistics as well with machine learning and other predictive models. They include tools that can deal with messy data, with unstructured data, with high volumes of data, and can generate insights, but also automate these insights across large populations. So for instance, if again, a comparison of a data science and a data analysis, a data analysis could just say 30% of diabetic patients had poor glycemic control, while a data science can say our model identifies high-risk patients 6 months earlier, reducing complications by 20%. So a lot more complex and something that you can contribute to a future intervention. And as there's a lot of data and a lot of resources available there, just a simple data analysis of the data won't make a huge impact if you want to especially publish your results, or if you want to contribute to the research with your findings. I'm going to show you a very simple data science process and for a simple problem and what that means. In order to move to the problem, I'll just show you the main steps, and we're going to look at that simple example following this step-by-step approach. So the first step is to begin not with the data, but with a question. I know many a times you look at some data you have about some patients, or there's a data in a repository somewhere and you want to make sense of it. But I would suggest to begin with a question you want to address, so with a question you want to answer, and then get the relevant data for that question. Say, identify a gap, identify a need, identify a problem, see how you're going to measure the outcome or the answer to that problem, and then we move on to get the data or to collect the data. You can either use existing data, as I said, there's some data sitting somewhere and nobody's looking at it and you want to make some sense of it. That's absolutely fine, but start with the question first and then see if the data is enough, or maybe you need more data or other data sets that could complement that data. Now, sometimes the data is cleaned, especially if others have used the data before and you're using it for a secondary analysis. Sometimes it's really messy and everything is collected and dumped there. Data is not consistent. Some measurements are missing for some patients. There's no standardization. You can have various measurements. Some could get a value between 0 and 1. Some could get a value between 100 and 200. And if you want to do anything with these types of data, the higher values will be more significant always than the lower values. Say any combination of these measurements might make no sense for the smaller values. That's why data is normalized, standardized, and kind of made uniform across all the measurements. You may identify outliers or some data that is not consistent across all the patients, so you decide what you're going to do with this data and so on. We call this data cleaning and pre-processing. Then you do this exploratory data analysis, which is basically data analysis, or you apply the statistics, inferential descriptive statistics to the data, just to understand the data, maybe do some plots, some visualization. This usually helps for generating hypotheses, especially the data visualization. As I said, I'm a huge fan of visualizing the data because there can be some patterns, or there can be some things that you can't see if you just look at a table of numbers. But if you plot them, or if you show them in a graphical and very much visually appealing way, you can see things that you can't see if you just look at the numbers. And this could generate more hypotheses that you could then verify with other tools, such as machine learning or other AI algorithms. I put this feature engineering here. We're not going to use it today in this example, but this is a very important step. And is usually useful if you have a lot of measurements and you know that combinations of these measurements are more useful than individual measurements. Say, for instance, I don't know, you combine two values together because you know they make more sense if they are together rather than taking them individually. This model selection and training actually refers to the machine learning model that you're going to apply for your data. A machine learning model is an algorithm or step-by-step process that starts from somewhere and gets to where you want to get to find some patterns in your data. Now, these models work in a way that we call train, validation, and test. So they train on some data, and training means you offer them enough examples to learn whatever relevant features they could learn from these examples, so whatever relevant they could learn from it. And then you test them on some unseen examples that are very similar to the ones you've provided when you train them. You measure their accuracy both on the training and the testing results. There are a few tricks that you need to take into account. You shouldn't be training too much because then it gets too used with that data, and it can work so well on the data it's been trained on, but won't work that well on the data you want to test it on. But there should be a balance and there should be a trade-off. When you're happy with some results on training, you test them. The validation is optional and is a step between train and test. Now, there are many ways in which you can split the data for training and testing. Usually is 80% of the data used for training and 20% for testing. But in machine learning, we usually repeat this process many times so that each data sample gets to be trained and tested. Gets to be in the training set and in the test set. So you never apply a model just once and you get the results. You apply them many times. We call this cross-validation. You apply the results many times by splitting the data, train, test in various ways, and then you average the results. And as I said, never apply a machine learning model just once. It may be that it doesn't work well at all, or it may be that it works so well the first time, but then it won't work that well if somebody else wants to reproduce your results. Always apply a model multiple times. And another advice, don't use just a single model. It may be that the model is not suitable for your data. You usually try a couple or at least 2 or 3 models and then compare their results. And maybe one of them is more suitable for the data you have than the others. And then you evaluate this model performance. We normally use a set of metrics to evaluate these models. The metrics should be appropriate for the type of learning you want to do. We'll talk about that a bit later, but it's very important to have the right metric to evaluate your model. Now, this is the simple example I mentioned, is diabetes prediction. It's an artificial data set, so it's no real data set. But we have a data set, as I said, begin not with the data, but with a question. And the question is, can you predict diabetes outcomes from just very basic patient data, such as age, BMI, glucose, and blood pressure? And for this, as I said, so this is the question, and I have an artificial data set that has 500 examples. 75% of the data is non-diabetic, and then 25% of the data is diabetic. As we saw on the previous slide, we only have a few measurements like BMI, glucose, blood pressure. We also have the age of the patients, and the outcome is a 0-1, diabetic or non-diabetic. Age is a parameter between 20 and 80, BMI between 18 and 40, glucose between 70 and 200, and blood pressure between 60 and 120. And this is just a snapshot of the table of the data. You see age, BMI, glucose, blood pressure, and the outcome, 0 and 1. And this is the first 100, or some of the first 100 examples. Now, if you remember, the first step was to start with a question. We had the question, can you predict the diabetic outcome based on those measurements? The data, we have the data now, and we're going to move on to steps 2 and 3, which was data cleaning and pre-processing, and then some exploratory data analysis. And I put these 2 steps together because there isn't much data cleaning to do. Data is kind of structured, it comes in a table. And due to the fact that you only have 4 attributes, there aren't much chances of having values or values that are not within the ranges. And this is some exploratory data analysis that you could see. So the top table just shows some mean standard deviation, first quartile, second and third quartiles of the data. So mean, max, standard deviation, and what those values are. And then is we also use the box plot of features just to see where they are, whether they are outliers. They very easy it's easy to identify outliers if you do box plots. They just come at the extremes. And then you see these correlation heat maps with red for positive correlations, blue for negative correlations, and then a range in between. Again, it's simple to visualize it because we only have 4 attributes to look at. And the last one of this exploratory analysis, and you see most of them, I've just put them visually, is this pairwise comparison. We have 2 outcomes blue and orange for diabetes and for non-diabetes, and this is the pairwise comparison between each of the 4 attributes taken together 2 at a time. Now, the next step will be feature engineering, and I mentioned that we're not going to do any feature engineering because you only have 4 features here. There's no point in combining either of them. But again, if you have examples with a lot more features, and there are many examples where we have hundreds of features, so hundreds of measurements, or even if it's less than that, in some cases, domain experts will know that a combination of 2 features or certain features could be more than 2. It doesn't need to be 2, it could be more than 2. But any 2 plus features combined will be part of this feature engineering. And as I said, experts will know that sometimes certain features taken in combination will make more sense than if you take them individually. And then the 6th step will be this machine learning model selection and training. I told you we need to split the data into train and test. Too much training will lead to overfitting. And I've just put here, I'm looking at the numbers, train and test 2080. 20 is for test and 80 is for training. I will change it in the slides. So too much training can lead to overfitting, and I said that means it works very well on the data it's been trained on, but doesn't work that well on unseen data or data you test on. There are various models that you could apply, and in machine learning we call these models like glass models or interpretable models or transparent models or explainable models. Means models that you could see how they produce the output. You could understand the step-by-step process. And there are some models that are black box models, so you won't know how they obtain the output. There's still a way in which you can at least partially interpret the outcome or the way in which they got to that outcome. But it won't be fully explainable, and that's due to the fact that these black box models, and in particular these neural networks, which is one of the most powerful machine learning models with deep neural networks and all the advanced neural network models, the fact that they are not interpretable, because usually you could if it's a simple model, the fact that they're not interpretable is due to their complexity, so they're very complex. And then due to the fact that they use, well, depending on their complexity, there could be up to millions of parameters that are part of the model. So even if you could see the expression they've generated, having millions of parameters is impossible to understand how each parameter, or even if it's not millions, but hundreds or thousands of parameters, it's really difficult to understand how each of these parameters that are generated by the model contribute to the final outcome. So we call them, as I said, black box models. I will still show you how you can apply a little bit of interpretability to these black box models by using some other models on top of the original algorithm. So interpretable ones, maybe logistic regression, you are aware of it. I'm going to use a model that is called the decision tree, and you might guess what it does. It's basically a tree where at each step it makes a decision based on some values or based on some comparison that is done at that level. Then random forests, basically a set of decision trees, but they're a lot more complex. XGBoost and neural networks, I mentioned, they're slightly more complex and they use more parameters. Now, a decision tree models for our problem with diabetes and the measurements we had for each patient could look like this. This is just the first 3 levels. Obviously, the more levels you have, the more complex your tree will become and will be difficult to visualize it. There's still some levels at which you could visualize a decision tree. So as long as you're happy with the complexity and could navigate it, just display all the levels. And you can see that at each step, there's a comparison, and then based on that comparison, there's a split. You see here Gini score that comes everywhere, and that is actually a value that is used in decision trees models that shows how a decision tree will be split. It has values between 0 and 0.5. A lower value means a better separation of classes. And at each node, the algorithm chooses the split that reduces this Gini value the most. A value of 0 means that all the samples belong to a class. And if you go back to this, you see that any end node or any node that doesn't have anything else coming out from has a Gini value of 0, except from Gini 0.33, which will continue in the next level, and 2.13 and 2.45. So this is like this because I'm only displaying the first 3 levels. Now, it's important to know what metrics you use when you evaluate your models. So for instance, in this case, we have a problem of classifying the patients within diabetics and non-diabetics. So in this case, we deal with a classification problem. So for a classification problem, there are various metrics, and one of the most used ones is accuracy. And all you need to know is these true positives, true negatives, false positives, and false negatives values. So true positives means the values belong to a class, and the algorithm classifies them as belonging to that class, the positive class. True negatives means the values belong to the negative class. The algorithm classifies them as belonging to the negative class. False positives means the algorithms puts them in the positive class, but they're not in the positive class, so it's false. And the same applies to false negatives. The algorithms puts them in the negative class while they are not in the negative class. This is all you need to know. And then there are various combinations of these 4 values that are called accuracy, and we'll go on with a few more. So accuracy is these combinations of true positives, true negatives. And the interpretation of the accuracy is that if you get a value of 0.5 or below, is not better than random guessing. So the algorithm doesn't do anything, basically. 0.8 means that 80% is correctly predicted overall. Now, this could be a combination of corrected predictive positives and corrected predictive negatives, but this works well when your data is balanced. Balanced means you have kind of similar representation of classes or types of outcomes into your data. So in this case, we have diabetics, non-diabetics. We have 75%, 25% is not that balanced. So we have a lot more diabetic examples than non-diabetic. So in this case, an 80% could be that or a 75% accuracy could mean that it classifies correctly the 75 non-diabetic patients, and none of the diabetic patients is correctly classified. So you need to be a bit careful with what accuracy means when the data is not balanced. In our diabetics clinical example, a classification of 0.82 means that it correctly predicts diabetes status for 82% of patients, but doesn't distinguish, it won't say how many, won't distinguish between false positives and false negatives. Another metric that we use is F1 score. And again, as I said, it uses true positives, true negatives. This time it uses these other 2 values that are precision and recall, or sensitivity and specificity, as you might find them. And then the F1 score will be a combination of this precision and recall. So what precision does, so precision measures false alarm rate. When the model says diabetic, how often it is correct. And in our example, if the precision is, say, 0.85, of 100 patients predicted as diabetic, 85 truly have diabetes, and 15 were false alarms. The recall measured missed cases. So what fraction of real diabetics did we identify? High recall means few false negatives. And in our example, a recall of 75 or 0.75, for instance, means that 75% were detected by the model as true diabetic, but 25% were missed. And then F1 is a balance of those, is a balance of precision and recall. And what it means, so if you get a value anywhere between 0.9 and 1, it's very good. Just a few cases are missed or incorrectly classified. 0.8, 0.9 is a good balance trade-off. It's not an excellent result, but it's an acceptable result. 0.7, 0.8 needs improvement, and I wouldn't recommend in any healthcare application to consider as a good result anything below 0.8. The usual literature says less than 0.7 unacceptable for clinical use, but I would say even 0.8 is unacceptable, and yeah, needs improvement. Now, if you have a high precision and a low recall, that means you have few false alarms, but or the algorithm had few false alarms, but missed 40% of the cases. A low precision and a high recall means it catches most cases, but there are many false alarms. Now, it depends again on clinical use. If you want to give a false alarm, I don't know what the costs will be and what the implications will be for all these false alarms. And a balanced F1 score 0.1 would be an optimal compromise. And another metric that is used for classification is this ROC AUC, or receiver operating characteristic and area under the curve. This is basically kind of the same thing. The ROC is a graphical plot, and the AUC is a number that kind of says what that area represents. And a value of, again, for this 0.9 to 1 is excellent, 0.8 to 0.9 is good, and I wouldn't consider as good results anything below 0.8 for clinical use. So remember, we had accuracy, we had F1 score, and ROC AUC. And now if we look at those, and if we compare based on those our models, we get the results in the table on the left, and then a graphical representation on the image on the right. And you see that, well, this was, as I said, a simple example and a synthetic example. So it wasn't very difficult even for these simple models to come up with very good accuracy and other metric scores. So most of them got very good results. Now, the neural network, you see, got the worst results there, but it is because they've used a very simple example of neural network. Obviously, you can play around with these models and you can improve the architecture. You can play with the parameters, fine-tune the parameters to work well for your example. I haven't done that. I've just applied them once with the same structure. Not once, I've applied them many times and averaged the results, but they've been applied with the same architecture. I haven't done any fine-tuning, any improvements. It's mostly just for showing you how they could be applied. Now, I told you that the interpretable models, obviously, you can see what they could do, and you know how logistic regression works and how you can visualize it. And I shown you the decision trees that we've got, but I haven't shown you the other models because you won't be able to interpret them. But for the black box model or for the non-transparent models, you can use some tools that can at least tell you what they do in getting those results. Two of the most common ones are this SHAP, and there's another one that is called LIME. And I've just used this SHAP model that is it stands for Shapely, Additive, and Explanations, and is a framework that is usually used for explaining model predictions. And what it does, it usually comes up with contribution of each of the features to the final outcome. So in our case, we only have these 4 measurements like BMI, glucose, age, and yeah. So what this is going to show how each of these features contributes to the final outcome, whether it contributes or not, because some may not have any contribution, but it can show you which ones of them have a higher or lower contribution. And if we look, I've used it even for logistic regression, for instance. So if you look at this example, just to exemplify it, what it means. So on the x-axis are features ranked by importance. So, sorry, on the y-axis. So the top one will be the most important one, and on the bottom will be the least important one. And on the x-axis will be a SHAP value. Positive value means increases prediction score. Negative value means decreases prediction score. You can see that glucose has a very high impact on the model outcome. It has red dots on the right, it has blue on the left. And now if we apply this to our black box model, so this is how it looks for the XGBoost model, for instance. We'll get similar graphs like this for neural networks and so on. And again, you could see here that glucose has a high impact on the outcome. Now, how we interpret those results and how we look at them. So it's not just, but when you do your data science projects, you need to interpret the results and then come up with some recommendations or come up with something. So, okay, we summarized, we had this data with 500 patients, 25% diabetic, 4 features, 4 features, age, BMI, glucose, blood pressure, 25 versus 25, 25 versus 75 distribution of diabetic and non-diabetic. And we had this 5 models we looked at, and 3 metrics, we compared them, and we used this 80-20 train test split. The key findings were that logistic regression and XGBoost outperform by 1 to something between 1 and 4% across the 3 metrics we used. Again, as I said, the models were just the raw models, not fine-tuned, not at their best. I'm just interpreting the results with these exact models that I've applied. Neural networks showed higher variation in predictions, and they were all simple models and could achieve 90+% accuracy despite being simple. And if we look at the feature importance and analysis, both using the SHAP algorithm as well as looking at the outcome of the interpretable models, we can see that glucose is the dominant predictor, followed by BMI, then age, and then the blood pressure is the last one and has a very minimal effect on the outcome. We could interpret it as the glucose testing being very important and should be prioritized. And maybe it could be routinely implemented for some patients, for instance, patients with a BMI higher than 25, or for patients with a family history of diabetics, or for some unexplained symptoms. So we could recommend a routine fasting glucose test for these types of patients. BMI had a non-linear impact, but still could be a target weight management for some patients. So for instance, with those with a higher BMI, higher than 25, focus on some exercise or some diet, higher than 30, maybe consider more advanced interventions. And could even take some actions and can embed one of these ML models into an electronic system that could flag high-risk patients. And I mentioned about this when I told you about a complete data science project and how it goes from having a data to providing analysis, predictions, and also an intervention. Now, some key conclusions and takeaways. when you have a data set to look at, or multiple data sets you combine or merge to look at, data quality matters most. So know your data quality if you can, if possible, to find this out. Otherwise, maybe even if you look with some exploratory data analysis, you can see the quality of the data. Data is the most important. And we usually say in machine learning that data is 90% and the machine learning model is 10%. And it's not just data quality, but also pre-processing of the data. Because if you don't pre-process the data and you don't put the data in a format that will be standardized, normalized, really ready for some analysis, then you won't get much of that data. So spend 90% of the time on having a good quality data, and then 10% on doing that analysis with machine learning or AI or whatever you want to do. Start simple when you want to use machine learning models. So don't use the most complicated model that exists. Maybe your problem isn't that complex. Start with a simple model. If you don't get the expected results, increase the complexity of the model or apply different models, but don't start from the beginning with very complex models, because it might make no sense. Compromise between interpretability and complexity. Remember, the more complex your model gets, the less likely will be that you will be able to interpret that model. So, decide what you want with your model. If you want an explainable model that can explain how it got that solution, then you won't be able to have it very complex, and you will need to compromise on complexity. Ask clear questions. And I get this many times. I see students wanting to do a research project, and they come with a question that has 3 questions in it. That's not a clear question. And if your question is not clear, then you might not know what to get from your machine learning or AI analysis of the data. So a clear question, you can follow up with more questions if you feel like you generate more hypotheses from the data, but be very clear with what you want to address. Don't be afraid of using AI or machine learning. There are also no-code tools. There are tools available for which you don't need to write the code. You just need to understand how to use them. Don't forget to focus on visualization. It's much easier to visualize things rather than reading numbers on a table. And it's very important to know how to translate the outputs to clinical terms. I see many times that a data scientist does analysis of a data and then with no knowledge about the domain. And then the clinical interpretation is maybe a lot more difficult or different than if an interdisciplinary team does that analysis. So if there is this exchange of information during the analysis, if the analysis is not done by whoever has the data and is knowledgeable of what is in there, then it would be good to have an intervention on the analysis process and interpreting the outcomes. And a few takeaways. Avoid overtrusting AI. It has some randomness in it. It does some learning. It could be biased, so don't overtrust it. Avoid ignoring the context. Say, many a times the context of the data of your problem is very important. And if you just look at the numbers, or if you just look at the text, or if you just look at whatever is gathered about that data and ignore the context, you might not get the results you expect. And avoid misusing metrics. I see this many times, that people use the metrics that are not appropriate for that particular model, and in which case you just measure wrongly the results of these models. Say the few things you need to be aware of. And I think my time is up, isn't it, Siobhán? But we still have maybe a few minutes if you're not running away for some questions.